We'll start just with quick slides on what is machine learning. I'm sure you know. I mean, in machine learning, well, it's something that went on for some time, but clearly, starting from 2012, roughly, there have been really an impressive progress. So it's a date in the sense that in this field they do challenge. So for example, there was a challenge which was visual recognition, in which you give different images to a computer, which means you just give vectors of pixel. And then for each image, you have a label, which is, it's an image of an airplane. So you put a label airplane and so on and so forth. And what you want is that this machine, if they get new images, they're able actually to tell you whether it's an airplane, it's a cat, it's a frog, or it's a horse. So there was this challenge that went on for some time, and there were several methods that were used. I think kernel methods were the methods that were winning for some time. And then in 2012, actually, the deep network, it was a deep network introduced by Inton that really, destroyed all competition. And then from there on, actually, the deep network always won, and they did many things, many breakthroughs, many things that were considered impossible with the previous method. So this started in computer vision, but now, you find machine learning, or what is called artificial intelligence, in society a lot, and you start to see it in science. While there is the very famous AlphaFold breakthrough for the prediction of protein structure. And then I'm sure that, one of the most impressive things is what is called generative AI, generation of text, so large language models like ChatGPT, that I'm sure 90% or more of you are using. And then diffusion models, which are, and I will talk more about them, that are used to create images, video, and sounds. And they're very interesting from the point of view of physicists, because they're really based on statistical physics, actually. All right, so if I have to do a kind of link between statistical physics, and in particular statistical physics of glass and disorder system and ML, you can see there have been roughly two different periods of time. So there have been a period around the 80s in which there have been, first a relationship with what was called a perceptron, which was introduced long before the 80s. And it consists, roughly speaking, to a neural network with just one node. And it was understood in this period of time that actually you can study this model using technique which come from spin glasses. So and concepts like phase transition, energy landscape, methods like replica method can be used actually to characterize the learning property of the perceptron. And then there is the other chapter, parallel chapter, about Boltzmann machine. So Boltzmann machine are, let's say, first generative models in which you have a probability distribution, like the Boltzmann energy. And then what you do is that during learning, you learn how to change the energy in such a way that the probability distribution, the Gibbs-Boltzmann probability distribution associated to the energy, is going to sample to produce typical configuration that are the configuration that you want. So imagine I give, images of cats, for example. They are not as good, but maybe images of numbers, and then I give it to this machine, and then in this machine you just change the coupling in the energy in such a way that at the end you have an energy such that if you just do a Monte Carlo Markov chain on this probability distribution, typical configuration would be, for example, number 1, number 2, and number 3, and etc. So these Boltzmann machines are very much related also to the Hopf model, and all this is related to the Nobel Prize of 1 year ago on relationship between physics and machine learning. So while this, let's say, is old history in a sense, interesting, and it's something on which so many of the techniques that have been used here are also used now by physicists that study machine learning. But really, the machine learning that is used now has, roughly speaking, nothing to do with these things. So nothing to do with restricted Boltzmann machine, and nothing to do with, let's say, 1 or 2 node neural network. So what happened starting from 2012 is that people started to use really massive data sets, really a lot of what it changed, really a big number of data, and over-parameterized models. So a model which contains a very large number of parameters and actually much larger than the number of data that you have. So typically something that if you do statistics, you shouldn't do, right? You never should use too many parameters, much more than the data that you have. And instead, these models really work in this regime, and they say you should work in this regime because they work better. Why? Well, that's one question that one would like to answer. So in this, after 2012, so the kind of machine learning models that have been proposed. So they work in a very different regime, over-parameterized, massive number of data. And then the two, let's say, the two really research axes that have been studied and on which there have been a lot of progress has been first supervised learning. So this revolution that started in 2012 was about classifying images, which is what is called supervised learning. And then there's been, more recently, generative AI with the generation of text, images, video, and sound. And so in both these cases, actually, techniques and methods that come from physics were useful to understand and to make progress on very important questions. And what I want to do in the following is to give you an idea of why these techniques are useful. And then for both cases, so for supervised learning and for generative AI, I wanted to present one question that has been addressed using this method, in which really the contribution of statistical physicists, in particular statistical physicists coming from this order system, was particularly useful. All right, so let me start with supervised learning very quickly, because I'm sure many of you know. So let's do the example with images, which for each image you have a label. Let's say the label can be, this is an image of a cat, it's an image of a dog, it's an image of an airplane. So an image is just a vector, typically in high dimension, because a simple image, I don't know, which is 100 by 100 pixel, it's a vector in 10,000 dimension if it's in black and white, and even more if it's in color. And then for each image, you have a correct answer. And then you have many examples. This is your training set. And what the neural network does is actually, let's say, very nonlinear function of many parameters, which I will denote W, such that it's a function of W and function of X. So if you give an image, and this function will spit out a possible value for Y, and what you want is that it spit out the value which is the correct one. So if X alpha is an image of a cat, and the Y variable, let's say, is 2 if X is an image of a cat, you want that the function gives you 2 if X is the image of a cat. So the network parameters, the things that you have to fix in order to have the correct answer are called, it's the weights, which are called W, and the goal is to find this function F that allow you to best classify the data once you have someone give you the training set of example. And so you use the training data set to learn, and then you take another set of data to test whether the system is working well or not. So of course, you don't use the same example that you give the machine to test the machine, but you use new kind of example. It's called a test set. So supervised learning, so the typical form of neural network are actually a collection, a hierarchical collection of perceptrons. So perceptron is just one node. And here you see you put node together with links. And so just to understand what these links are, so just one given node working this way. So from each node you have an output, which is called H. So these are the weights. So you multiply the H with the weight, and from this it gives an input. You do the same thing with this one. You take the H multiplied by W, and you insert it here. And so this is what you do for all these three incoming vector, or these incoming arrows. Then you can shift a little, you can do a shift. And this is what actually, and then you put this into a nonlinear function, which typically is the same, it's kind of sigmoid, it's the same for all nodes. And this will spit out actually an output. And so you do this again and again and again. They're called deep network because they have many nodes here. And so let me go it here. You have many nodes, and then you have many layers. And what is thought is that these many layers actually are able to learn a hierarchical structure in the data, and there are actually proof of this. Okay, so this neural network at the end is just a very complicated nonlinear function with a precise structure and with a lot of parameters. Okay, so when you do, let's start to see why there is a connection with this other system. The idea is that when you want to learn, someone gives you a lot of example. And what you do is you define a cost function that you want to minimize, such that if the cost function is 0, it means that you give the correct answer on all the example that you give to the model, you give to the system. So here is an example. So you make a sum over all example alpha. Alpha goes from 1 to m. And here you have a L, which, for example, let's say in the simplest case, you can take this way. It's y alpha minus f. So remember, for each data, you have a correct label. And so if the output function of the neural network is the correct label, you get 0. If it's not the correct label, then you get something positive. So if you get a loss function which is 0, it means that the neural network answer always the correct answer for all example. Now, if you think about this, it turns out that you can interpret this as the energy function of a disorder system. Why an energy function? So the WR, the degree, will be the degrees of freedom. And then the Y alpha and the X alpha are given. So it's like really like quench disorder in a spin glass. And indeed, if you work a little bit in the simplest case, actually you even find actually couplings within the W which really resemble a spin glass. So in any case, well, if you want to study, for example, the property of the loss landscape, it's really like a spin glass. You have to do it for a quench configuration. So for someone give you the data, for a given Y alpha, for a given set of Y alpha and X alpha, you want to study, well, if there is only one minimum, if there are many minima, and how is the dynamics in this loss landscape, because when you want to train the model, well, you have to minimize this function. So typically what you do is that you do gradient descent. So what they do to train, indeed, they minimize the loss function. You can either do simple gradient descent, or actually you do something which is called stochastic gradient descent. It means that here you do, well, this is discrete version, so it's gradient descent. You change the W. Here you have, let's say, it's called the learning rate. Is related to delta t. It would be related to delta t. And here in this sum, instead of summing on all alpha from 1 to m, at each step of time, you take just a batch of the example. And then at the other set of time, you take another batch. So this is called stochastic gradient descent. If you take b of t equal to m, then you take all the example at once. But the problem is that typically you cannot do it because you have so many examples that you will never be able actually to perform this sum. So this is why they do it. It's in a practical way. But there is also many people that think that actually doing this stochastic gradient descent is actually better. So it helps you to find better minima. Yeah. So I think so the reason is that what you do in machine learning is that, which is different from physics, is that you minimize the training loss, but what you really would like is that the system is minimizing the test loss. So it's minimizing the loss on sample that is never seen. And so taking this introduces stochasticity, which makes that actually you are better in minimizing the test loss taking stochastic gradient descent, which is really what you want. If you really want to minimize the training loss, then you should take the gradient, but it's not what you want to do. Okay, so first also why there is a relationship with physics, and one of the reasons is that, as I told you, starting from 2012, people use many data and very big networks. So which means that you have a lot of parameter, a lot of degrees of freedom. So when you have to minimize this function, it's a bit like what we do in physics and in disorder system in particular. You have a complex function with a lot of variables. And just to give you order of magnitude, and these are, let's say, order of magnitude within the simplest system ever. So it's a very simple image, black and white, very small. I mean, the image vector is already 1,000 component. And then the typically used, the data set is 100,000 images, and then you typically use a deep network which can have 10 to the 8 parameters. And this is really the simplest case. So just to give you an idea, I think ChatGPT, so GPT-5, the number of parameters, it's not known because it's not public, but roughly it's of order of trillions of parameters. So, well, this gives you the idea of the number of degrees of freedom. Of course, I mean, in physics, we have 10 to the 23 parameters, so much more. So but still, I mean, trillions of parameters that you have to optimize clearly, well, makes the problem interesting just to know why is it possible. And also, well, the clear question is also why actually it's good to use more and more parameter given that the data is what it is. So you use much more parameter than data. And what has been understood, so this was at the beginning, and this was then studied a lot in recent years, is that given a problem, so this is, I think, is the same problem of 2012, so it's a classification of images, the bigger is the network, the better is the accuracy, which again defies all statistics that you learn at school typically, in which they tell you if you have a certain number of data, you shouldn't use too many parameters, otherwise you will overfit wildly and you will get a wrong answer. And here instead, if you talk to engineers, I remember when I started to work on this, they say, no, it's good because you have many parameters, so you have less barrier in the training loss, and then actually generalize better. Okay, why? So this is one question that I would like to address. So now, relationship with statistical physics, in particular with statistical physics of glassy system. Well, first, here you have a larger number of data and parameters. So here we deal in typically is the large number of degrees of freedom. In this case, you have a complex high-dimensional loss landscape. Again, the loss landscape is created given the data. The data acts like a quench disorder, so you can think that indeed it's complex and then has been studied, and it has been shown to be very complex with a lot of, I will come to this later. Well, in physics of disorder system, we know, I mean, it's in glasses or spin glasses, we know that the energy landscape is particularly complex and have a very interesting organization. And here, the thing which is really interesting is the way in which they train the system. So they do this stochastic gradient descent that you can think it's a kind of version of Langevin equation, even though it's not exactly the same, but it's similar. And actually, it's very similar to what we study when we think to glasses, in which we decrease the temperature and then the system has to go down in the energy landscape and reach maybe a minimum or reach some low energy state. And so try to understand what happens with this, or what is the property of the landscape and what is the dynamics in this landscape is something on which people have been interested a lot in the case of glasses. And of course, people have been starting from, I would say, 2015, people have started to study a lot. So the first thing was people didn't believe how it's possible that this system that should have a complex landscape could actually be trained and work, because why the system is not blocked somewhere. And so many people ask and study what are the properties of the landscape, using ideas also that come from the physics, for statistical physics. Then there is the big question about training dynamics. And so for all these kind of questions, indeed, methods and ideas from statistical physics were useful. I mean, of course, there have been other ideas coming for computer science, but there have been ideas and methods from this side that were useful actually to address these questions. And actually, there is another question which is not common to statistical physics, but it's very important in this case, which is the one that I would like to tell you more about, is why over-parameterizing is beneficial, which to me, at the beginning, when I started to work, was one of the big puzzles. Why if you over-parameterize like crazy, actually is good instead of being detrimental. And just to say that the methods that now are used in theoretical computer science to address this problem, of course, they have their own method, but methods like replica, or what is called Katz-Rice, which is the method to compute minima of complex energy landscape, and dynamical mean field theory that have been used a lot in the physics of disorder system and glassy system, now are used a lot in this field, and probably actually they are more used there. I think replica and dynamical mean field theory are more used there than in physics right now. And you can find actually a nice paper in which mathematicians prove bounds, and then they have in the appendix a replica computation, and then they say, well, the bounds is not really matching the replica, which is not rigorous, but probably means that the bounds is not tight. And other things, I mean, dynamical mean field theory is currently done by people that has no background in physics. Okay, so, this was to give you an idea of why there is a relationship. So there have been many works around these questions using methods and ideas from statistical physics. What I would like to tell you quickly is the question of the answer to this question, and how actually ideas from physics and physics of glassy system play the role. So, okay, why over-parameterizing is not harmful, and actually is good for deep neural networks, something that was clear to the practitioner from the beginning. Okay, so what would be the reasonable expectation? What we would do as, in a simple-minded way, and then which is actually, done in a very, let's say, theoretical way in statistical learning theory, is that if you plot the error that you do when you do a fit, because at the end it's nothing more than high-dimensional fit, supervised learning, is that, if you have many points and you use very few parameters with respect to the data, except if you exactly know what is the law from which the points come from. But if you don't know and you have not many points, you will make an error. Just because, imagine here, if I have a curve which is like this, from which the points come with some fluctuation due to some noise. If I just go with a straight line, just 2 parameters, then I will make an error. So if you don't use many parameters, you have a big error. Now, if you use too many parameters, this is the standard expectation that you have from statistics, then you are going to overfit. So, I mean, the curve that you will get, it will go almost through all the points in the training set. But then if you take, when you test it on the test set, which is so other points, then actually it will be very bad. So it's typically, this will fluctuation will give you a very bad result. Yeah?
So the error in the latter case is with respect to other data, right?
Yeah.
Because this data is not well defined.
So exactly, so this means that, so this is the training set, this is the training set, and then, the error is with respect to a test set, so a new set of points. Generalization, exactly, generalization error. So you expect typically that roughly there will be a sweet spot in which the number of parameters is roughly the number of data, in which is where you should, the number of parameters that you should use is where the generalization error should be minimum. Okay, so this is what you expect, and in general, if you do a fit with not many parameters and not many data is what you find. Now, what you find in reality, that's the, again, is the generalization error. Look at the blue curve. So the blue curve, it's a very simple, actually, a classification problem with images using some simple network like this. And here you have the number of parameter on the axis. Here is the generalization error on the y-axis. And the blue curve, so what it does is that it starts to go down, as you would expect. This is because you have less bias. But then at a certain point, it goes up. It has a peak, which was kind of unexpected for the people in the field. And then the most interesting thing is that it goes down, 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 down. And now what I put here as a line is the line at which the training error, here is the point where the training error goes to 0. So this is the training error. Training error goes to zero at this number of parameter, which is here. So it means that on this entire regime, actually the training error is 0. So you fit all the data. But you see that the more parameter you use, actually, the more actually the accuracy is going down. Yeah.
What are the blue, green, and what are the 3 lines?
Yeah, so I will tell, so the blue, well, is what I told you, so is the generalization error. So the green is the same thing when you put a regularization. So it means that, so it means that this peak is actually, it can disappear if you put a regularization. And this one I will tell you later.
And all of these are training errors?
Sorry?
All of these are on train set or test set?
So all of these are on the test set, except this one, which is on the train set, which is just a zoom. Okay, so this, well, so actually, so the fact that there is a peak here, is something that we could explain using statistical physics. And here actually has a nice relationship with the jamming or the SAT-unsat transition. So the idea is that when you do the fit, when you learn, well, you have some kind of constraints that you have to satisfy. So these are, if you remember, is the y alpha minus f square. So you will like that all these constraints are put to 0. And so what happens is that when you move this way, actually, is a little bit like approaching the jamming transition. So at a certain point, so the jamming transition is similar. You have constraint. You don't want overlapping particle. And then if the density is too high, well, you undergo the jamming transition, which is where you have this SAT-unsat transition. So you have a satisfiability, unsatisfiability transition. And so we make a connection, actually, between this transition, something that you have here, the fact that when the training error goes to 0, this should be where this transition takes place, and the jamming transition of ellipsoid. And this, exactly like in the jamming transition, you have critical properties, so we expect actually to see a peak like this. And this was an explanation, and actually, of this peak. Well, we try to put this forward in the computer science community, so they like the peak, but there was a paper at the same time, and instead of calling jamming transition, they call it double descent curve, and so the jamming was completely forgotten. And this is what is called now in the literature, is the double descent. Double descent in the sense that you would expect a U-curve, but the curve goes up and then goes down again. Yeah? Sorry? Yeah. Yeah.
I think that was kind of the same question. So on this side of it, I'm satisfying the geometric, the
Yeah.
hard sphere constraint in some way, or the hard ellipse constraint. And then on the other side, I'm developing more and more states of.
So this side would be the low density, and this side would be the
I
high
see.
density.
Okay. So this is coming to the
Yeah.
ellipse jamming transition. And on the other side, how do I think about it then? The low side then.
This one?
Why is there a peak?
Why there is a peak? Well,
like-
it's because you have a lot of fluctuations, and actually the solution that you get is going to fluctuate a lot, depend from one data set to the other, and these
Okay.
are related to the
Okay.
fluctuation that you have at
Okay.
jamming.
Okay.
So,
Well, this is a little bit technical, so we can discuss maybe later.
but,
Yeah.
so, I mean, yes, I mean, in some sense, if I put it very bluntly, learning is about the ability to generalize and not to perfectly fit the training data.
Yeah.
Right, and so that's why, in some sense, it's up to by zeroing the training data, you basically can reproduce it. And then you're bringing in additional degrees of freedom somehow to have the flexibility to actually generalize from this or to account for something that...
I mean, it's the usual explanation was that it's good to have less parameter than data.
I know, but...
So that in this way, I mean, let's say you average out some noise and you really learn well the parameters.
But if you had some kind of way of measuring a generalization error, clearly what you would want to minimize is the generalization error, except that that's kind of, that you cannot sum over as something because, it has to capture everything that it could be generalized to, right?
But you see, I mean, if you do it in low dimension, this is what you have. I mean, if you go all through all the points, so the function is going to do like this, then you take new set of points, and it's going to perform very badly because it will be very different from what it is. So in principle, I mean, it's really puzzling why this curve goes down when you are in this regime. And indeed, at the end, it's not the peak. I mean, it's not that important. The real big question is why this curve is going down. So why putting more and more parameter is good? Okay, so now why? So there is okay, let me tell you. So the way in which people have studied this problem, it's again really like in physics, and there have been statistical physicists working on this. So you could do simple models of neural network, and this has been done. So you see, it's not now one perceptron. You have many. At least you have one hidden layer with many nodes, and then you can use technique like replica method, random matrices, or rigorous method to study. I mean, exactly the problem before. So you can even reproduce this kind of curve to understand why it goes down. So this was one approach. There is another approach which corresponds to take an infinite large hidden layer, and it's called neural tangent kernel. And again, you can study either with rigorous methods or with statistical physics, or you can do numerical experiments. So now, what is the explanation of this, which I like because again, there is a lot of dynamics in this study of neural networks, and I think this is also a reason why statistical physics can give interesting answers. So the error, as I told you before, there is a bias part and a variance part. So the bias part is just if you don't have enough parameters, then you have a bias, and so you may have an error. But now so let me maybe go back to this. Here you have a part which is called the variance. It means that the function that is represented by the neural network can fluctuate a lot because for one training set, you get a certain function. For another training set, you get another function because it fluctuates. Now, what happens for this big neural network, what has been understood is that, so what happens is that you have this, let's say, loss landscape or energy landscape, which is complex in the sense that this has been discussed a lot. You have bad minima, but even if you have bad minima, actually, when the system is over-parameterized, you don't see them, and the system actually goes down to what is called the zero energy loss or zero loss manifold. You know that we have a zero loss manifold just because you have so many parameters that there are many ways actually to satisfy the constraint. And so what happens is that if you start from a certain initial condition, you will go in one point. You start another condition, you will go into another point. And what turns out is that the error that you do, it comes in a big part by the fact that different actually initial condition bring you to a different function. And so actually in the regime, in this big neural network, so the error is due to the variance which correspond to the initial condition, not much to the fact that you see different data. And now what happens is that what has been understood is if you take the network bigger and bigger and bigger and bigger, actually you will reduce this fluctuation. So the system, what you see, and you can see it in this way, so this has been done either analytically or numerically, which is this curve. So imagine that instead of taking a big network, you take many small network with the same, such that if you sum the number of nodes, you get, the same number of nodes, okay? So you are just, in a certain sense, averaging neural network. So what you see, this is the is the error that you do. So what you see is that in all this regime, if you average over different networks that are trained with different data, then what you get is that you get an error which is much, much smaller. So now the interpretation and what you find is that it's a kind of self-averaging. So since when you take the network very big, actually the different part of the network, it's like taking different initial condition. And then when they come together, they just averaging their response. And so they just kill the fluctuation, which I told you here, which is the one which is responsible for the error. So at the end, it's important, the structure of the network, because it's thanks to this structure, which is modular in this way. And thanks to this modular structure, well, there is a kind of self-averaging, which is called, it's a kind of self-averaging, which is called also ensembling in the case of neural network. And this brings the error down. So the reason, at the end, the reason why actually taking more parameter than, much more parameter than data is good, I think is there is one which is we don't understand fully, but seems to be there, which is that the more parameter you take, the less bad minima you have. So when you go down, you are not blocked on minima which correspond to bad generalization. You just go to the zero loss manifold. And then the more parameter you take, so the bigger is the network, the more actually you average out the fluctuation, which will produce a variance and would give you an error. So this is something in which really, physicists really have contributed a lot with, again, with methods and idea which come from physics of disorder system. Okay, so this was for the part on supervised learning. And now what I would like to do, so when I have to stop?
Another 30 minutes. So,
okay, good.
Is this analogous to the sharpening with system size?
Yes, it's similar. It's the same phenomenon. So it's the fact really, in a certain sense, in physics, by the way in which the system interact, the more it's bigger, the more the fluctuation goes down. And here is, by the way, as is the architecture, it's the same thing.
If you increase the number of parameters, would the blue curve decay in a way that you understand?
Yes, so this decay here is known analytically.
Okay.
So this decay one can predict with this idea. Yeah. Now there is still a question, which is why the asymptote here is small, which really means why the system. This tells you that taking a bigger system is better. It doesn't tell you why. I mean, the system, a very big system, is answering in a good way. This is still, of course, an open problem. Yes. Why the asymptote here is small? Yeah, it could be.
Why plateaus at point?
Exactly. Exactly. This is a big question, which I think has, again, to do with the architecture of the network and the structure that you have in the data that you are that you want to work with. But it's not understood. That's something which is completely open.
But is this a sort of a general numerical value, or it would depend on the 0.050 something?
So the value here depends on the network, and on the data. But the fact that it goes down to a value which is very low, this is very general.
So what determines this segregation length that they split into these different small neural networks?
So this is just a trick. So this is a trick to produce this curve, just to show you that the effect of collecting together a small network will give you this curve. But in reality, I mean, here is, when you take the system bigger and bigger, what it's doing is practically doing this, except that there are also cross-links. So there will be link which go here and link which go there.
Architecture in the data, is there some length scale that makes it valid?
Yeah, well, So it's difficult to talk about length scale. So it's true that there is a characteristic size this goes down as a power law, and with associated to this power law, there is a characteristic, well, you can call it characteristic length, but there is no study of, let's say, length scale inside the network. So, okay, I would say, no, it's universal. It's the one here, if you so it depends, it may depend on the way in which you initialize the weight in the dynamics. But if you take a certain type of initialization, then the power law is fixed.
So can you say a little bit more about why this is like self-averaging?
Well, so the idea is, when you have, the idea is that, let's say, you have a, how I can say it. So when you have a big network, and so the big network receives the data, well, you can think that in a sense, actually, while different parts, I mean, when the data arrive here, so these different parts are taking like different initial condition in a sense. So it's not that easy because then they are cross-linked, but in a sense, really, taking a bigger network is like looking at more data at the same time.
Can you say that there is a finite correlation length, and then when you have many of those, then it self-averages, you know?
Yes, yeah, that's what I
I
was
think
saying.
is the concept, right? That there is a typical correlation size between these many parameters. It's not that you're really increasing, you're just doubling and tripling and quadrupling, and then you'll have, of course, the effect of self-averaging.
Yeah.
Right, this is what you want.
Yeah. Even though, I mean, this length is not computed really.
No,
I
but
mean,
that's the
about-
idea,
Yeah,
I
that's the
guess,
idea. Yeah, that's the idea.
So the parameter size, I guess it's in reference to the image size or the sample size, which is the operative sort of what's like the correlation length.
That's what makes it precise.
Yeah.
I think it's the data. It's the size of the data. Yeah.
It could be the ratio of parameter to data.
That's what.
Parameter to data. Okay, this I should. No, I mean it's parameter to data. So So first on this axis you should do parameter over data, but then indeed if you change the dimension of the data, then this plays a role. Yeah.
So I'm having a little difficulty understanding the green plot specifically because if it is a regularization, I mean, if it's a regularization, then it should not matter whether you increase the number of parameter. I mean, they should go to 0 because I'm assuming you're using an L1 or L2 regularizer, right?
Well, actually, this regularization is just early stopping. So you're stopping.
I
first
see.
dynamic.
Oh, it's not an L1, L2
No.
regularizer.
So actually, just to say that this curve that you see here, you really have to leave the system trained for a long time to develop the singularity. Yeah. Okay, so this is the first part, so supervised learning. And now there is another part, which is generative AI, which is more modern, I mean, more recent, let's say, even if all this is recent. And generative AI, I mean, to me, it's really more spectacular than supervised learning. So in generative AI, you have generation of text or generation of images. So here, well, this is something that I did actually for the conference 1 week ago. It didn't change. So I asked ChatGPT to write this English sentence in a poetic way, either in French or in Kannada. So this I cannot judge, but Shri seemed to say that it was good. And this in French is kind of good, I think. Maybe it's not fantastic, but it's kind of good. In any case, it's impressive, and I'm sure you have used ChatGPT for more serious stuff than this. And then in images, well, example is image. You can create images of person that do not exist. You can give a prompt and say that you want to see an angry bird, and here you see it's impressive that the machine understands what it means to be angry to you. It's angry, this bird. You can use it to create videos and now actually to create songs. Now, in this generative business, there is there is a big relationship with statistical physics. And the reason is that actually it's very similar. It's a very similar problem with a twist. So in the case of generative AI, so what you have, let's say, a set of images, for example. a lot of images in large dimensions, so a lot of images in large dimension, and the idea is that you give it to the system, and what you want is that the system will give you a new image that you have never seen, but which has the same statistical property of the one that you gave it to him. So what it means, generative AI, at the end, in essence, it means that you have to learn and to sample a high-dimensional probability distribution, and what you get is just data. You don't know the probability distribution, you just have data. And it's important, it's very high-dimensional. This is what makes the problem difficult, and the fact that there is a solution spectacular. Now, if you think to physics, well, it's the reverse in a sense. So what we also deal with high-dimensional probability distribution, so we have a lot of degrees of freedom, more than trillions. But we know the difference that we know the probability distribution in many cases, at least. For example, the Gibbs-Boltzmann distribution, for which you know an energy function. But the fact that you know the probability doesn't mean that you know what the system is doing, and it doesn't mean that you know how to sample from this probability distribution. This can be very hard. So in a central sense, in this problem, it's a problem of you have the data, but no probability laws, and you want to learn and sample. And here you have probability laws, but in many cases you don't have the data, or you can have some information on the data, for example, from experiments. And then what you want is you want to characterize the system, so many properties of the probability distribution, and you want to get new sample if you want to get to do numerics. So while you see, I mean, the system has, clearly it's a problem with an overlap, even though there is a different perspective. And there are many things that people do in physics and find in physics, like emergent behavior, universality, and phases, that you find in physics, but you can find also in AI. And something that I will tell you in a minute is that, for example, a generative AI system can work in two different phases. They can work in a phase in which they just memorize the training set. So if you give a training set and you say, create a new image, I don't know, of nice people, and then it gives you just an image that that it was in the training set. So in that case, they are not generalizing, they just memorize the training set. Or they can be in another phase in which they really work and they really give you a new image. So, and these are really phases of the system. Exactly like in physics, we have different phases in nature. And then again, methods that we use in physics, thanks to the fact that you treat in both cases high-dimensional probability distribution, actually methods developed in physics are useful to understand problem in this field. And so, while it's I would say again, this is something which is, I'm repeating myself. I mean, you can do a theory of generative AI and machine learning algorithm using methods that come from statistical physics, because while you deal with similar problems, and of course, something which is always very important is trying to understand the training dynamics, but then you can, and training dynamics, you can think it as an out of equilibrium dynamics in physics. But then actually in the case of generative AI, there is one part of generative AI, which is the generation of images, video, and sound, which goes even, I mean, way beyond this. It's just that the way in which you generate these images or videos is really using statistical physics. And this is what I want to explain to you, which is something on which I started to work a few years ago. Because, I mean, if you think that the images like this, or well, if you play with song and video, just use, as I will explain, they are just produced, just running a Langevin equation. And so these diffusion models that have been, became the state of the art starting from 2020 to generate images, audio, and videos, are really based on physics, actually out of equilibrium physics. Now they are in state of the art. I mean, diffusion models are variant. You can use it for images, text to image, sound, video, while you can try to use it to do science. That have been used, for example, to produce Lagrangian turbulence configuration. Then you can try to use it to do sampling. So, well, Ludovic, I think, will talk about this partially tomorrow. Okay, so well, now I want to show you what they are and why they are, I think, so nice for statistical physicists, especially statistical physics that work on out of equilibrium physics. So the idea is the following. So you have a set of images, let's say images, but can be whatever. I mean, it's again. And actually now people are also starting to use them for text, like for example, for GPT. I mean, it's like GPT. So you have a set of images, a mu. Again, they are in RD, vector in RD. You have many of them. This is the dimension of the data. N is the number. And the idea which is behind is the following. So imagine, so if when you have an image, so each image is just a set of pixels. And what you do is that, so X is, so you run this Langevin equation, which is just Olstein-Uhlenbeck equation, very simple. T is the temperature, let's put it to 1. They put it to 1, typically. And you start at time t equals 0, you start from an image. So each pixel now is just running with this Langevin equation, which means that it's just a particle in a well. So at long time, which is not so long, because this converges very quickly to equilibrium, the system, each pixel converges to equilibrium, which is just, it means a particle in a well. And so a particle in a well, in a Gaussian well, it means, sorry, a particle in a well, it means that the probability distribution is a Gaussian. So what this means is that if you run this Langevin equation starting from a mu, which is data, so let's say this nice picture of a dog, you run each pixel, and each pixel go to a Gaussian variable, independent Gaussian variable. And so what this diffusion model do is that learn actually how to reverse the process in a stochastic way. So which means is that imagine now that there is a stochastic process, and the answer is yes, it's known that there is a stochastic process, such that, so here you have a stochastic process that goes forward in time, and then you have a stochastic process that goes backward in time, which is just the time reversal of the forward one, such that if I start from the probability distribution that I have here, which is that's the probability distribution of white noise, is going to recreate the probability distribution that you had here at the beginning, okay? So if you knew this time reverse stochastic process, now you can take a new white noise configuration, you run the backward stochastic process, and from this you get a new sample of the original probability distribution. So if at the beginning you have a probability distribution which is the images of dogs, while what you get is the new dog. And so this is really how it works. So what this model do is that they learn how to go backward in time, and then what they do when they create these nice images, they really run a Langevin equation starting from white noise, which again, if you're a physicist and you work a long time on Langevin equation, is kind of incredible.
Why does it form a dog and not a horse?
Okay, exactly. So let's start to discuss this. So the first thing is, what is this reverse process? So this reverse process is something which was well known in stochastic processes, that if I have a forward process, which I just defined here, so you start from a certain initial probability distribution, P0 of A, you go forward. So if you want to go backward, so there is a Langevin equation, a backward Langevin equation, in which you can write this way. So tau is the time running backwards. And what you have to do, so here you have, well, the same potential with a minus sign of the Olstein-Uhlenbeck, but especially what you have a force field, f of I, that you have to insert in order to go backward. And this force field is what is called the score, is the gradient of the log of the probability pt of x. So this is the probability, is the probability that you have reached here along the forward process. So let's say if you want to go backward, what you have to do is that at each time you have to use a force field, which depends on time. And the force field here is to get it, you have to know the probability distribution, how it evolved until time t along the forward process. Then you take the log, you take the gradient, and this will tell you what is the force to use here to go backward. Of course, this force field is evolving with time. Now, so why gives you a dog and not a horse? If you train only on images of dogs, then what you are doing is you are, let's say, transporting the probability, which is the probability of, in principle, of dogs to white noise. So this is what you learn. So what happens is that, so this thing here, in principle, you don't know it because you don't know the initial probability distribution. The only thing that you have are trajectories. And so there is a nice, well, a way to, so what you do is, again, you write a cost function or a loss function in which you have here a parameterization of this score with a deep net, with a lot of layers and a lot of parameters. And you can transform, just by an integration by part, this loss function in something that you can evaluate using a sum over trajectories. So here you have A, which is the initial condition. X is the position at time t. So what it means is that if I want to learn the score at time t, I have to minimize this loss function. And this sum here is going to be the sum over all trajectories. And at time t, I have to know what is the x at time t, I put it here, what is the a, which will be the initial condition, and then I sum over trajectories, and now I have something which I have to minimize with respect to the parameter, and in this way, I get the estimation of the score. And so, well, this is how it's done in practice. So this is, you have many trajectories, many data, many trajectories, and from this you learn the score which is associated. And once you know the score, then you know this force that you have to use to go backward in time. And in this force, I mean, even when you go forward, all the pixels are going forward independently, but when you go backward, this force actually, it makes all the pixels interact, and this is why you start from white noise, and then it gives you a nice figure. Yeah?
Use Untitled because you know the propagator, so you can calculate this. But I mean,
Exactly.
what happens, I mean, in general, I mean, you can have a, different process, right?
Yes, so but it's not studied much because indeed the thing is Einstein-Uhlenbeck. The nice thing is that the forward is very easy and you use it a lot. So something that one can do is to make a twist on at least you use Einstein-Uhlenbeck, but for example here it's not isotropic, and here you have a covariance which is not isotropic. Maybe you can have not a delta function, and even this is just started to be thought about and start to be used now, but people didn't explore it. And you're right that one could try to think, I think, given the data that you have, maybe there is a forward process that is better suitable, but these kind of things, for the moment, people didn't ask. But I think it's a very good idea. Okay, so now again, to give you an example of something that one can do. So already here, I mean, this entire, let's say, generative AI of images, and video and sounds is really based on physics. And indeed, the first paper, it's a paper by physicists in 2015. They put out the idea, but then it wasn't completely clear how actually you estimate the score in a good way from data. And then started from 2000 and let's say end of 2019 and 2020, so it was clear how to do it, and people in a certain sense reinvented it partially. And then from 2020 after, it's the method that has been used by everybody. Okay, so, well, to give you an example of things you can do now, I think it's with the fact that the generative process is just dynamics out of equilibrium based on a Langevin equation, then of course I think ideas and intuition which come from physics can be useful. And so just to give you an idea of something that we did, is that what you could ask is, imagine that you have, just to be simple, imagine that you have, you train the system on two sets of images. So here would be images of, I don't know what it is, bear, and seashore, for example. It could be cat and dogs, but it's not cat and dogs. I think it's seashore and some kind of animal that I don't remember. It could be a bear, probably. Okay, you have two classes of images. And now the idea is, when you go backward now, you start from white noise. So this is an example in it's an illustration in two-dimensional to make you understand what happens. So during the backward trajectory, I mean, some trajectory will give you a seashore, some trajectory will give you the animal. So how it works, when the trajectory decide in a certain sense to give you one and not the other. And so what you can do, solving simple model and then testing in numerical experiments, what happens is that there is really a phase to dynamical transition out of equilibrium during the backward process. And one way to understand is that actually the force field has a kind of symmetry breaking if you have just two classes, like in physics, in the sense that you start at the beginning and the force field corresponds to a potential which is just one well. And then actually the force field is such that you start to have two wells, which becomes deeper and farther apart, and which actually are bringing the trajectory toward the correct probability distribution. So here, the idea is that at a certain time during the backward process, the force field change has a transition, and then you have, well, some trajectory that are brought to seashores and some which are brought to, well, this animal that I don't know what it is. So this kind of transition now, it's been seen in numerical experiments, and it's clear that you have, for example, even if you have an animal, which given the same, you have different species of the animal, and then you can have different colors of the animal and different other. And so in this case, this trajectory, this transition that you have here, actually, you can have a subsequent transition corresponding, for example, I don't know, you can have, first you decide to have predator instead of non-predator animal, and then within the predator, you can have, I don't know, wolf, and the leopard, and then between the leopard have different colors, and all these correspond to different transition that takes place one after the other. Yeah.
So is there an equivalent of the memory capacity in Hopfield networks that this might have?
So, yes. So this is related actually to the second transition. So this transition is a transition that you really understand using physics idea. And there is a second transition that you can think about, which is now, so this, what we did in this work was to study thinking that the neural network is very good and you optimize, and the training was very good. So we are not thinking that maybe the model is not good enough. So even if the model is, so it's very good. So what happens is that after a certain time, since you have something which is called memorization, and so let me explain what the idea of memorization is that when you train a system and you give a certain number of example, so it's like if you have given to the system a probability distribution which corresponds to a sum of delta peaks, where each delta is on an example. So this means that if the model really works as it should mathematically, what it should give you should give you back one of the example in the training set. So, and this is what you see is that when you are going backward in time, there is a regime until which actually the system is not really correlated to the training set. But then actually, after a certain time, really the force field is just pushing you toward an example. And this is the time scale at which this force field is pushing you. And so at the end, the system, if it was perfect, it will always memorize. And this can be understood actually using techniques from disorder system. And actually the transition that you have here is really like a glass transition, in the sense that you have a landscape in which all the minima correspond to the data that you have used to train the system. And when you arrive here, well, you have a force field which corresponds to a probability distribution, which is at very low temperature, which is just pushing you toward one of, let's say, of the glass, of the ideal glass of the system. So now,
yeah, I think I probably missed something like this. For example, in this diffusion models, like this previous example when you said like this process, let's say you model by a Ornstein-Uhlenbeck process. So then you know the propagator. So what is this learning process? I missed it because.
So the learning is when you have to learn this core function, which is here. So what you have to you have to learn. So you have a model for the grad of log pt of x.
Okay. But that you are taking to be this Ornstein-Uhlenbeck process, no?
So the Ornstein-Uhlenbeck process is the forward process.
Forward process.
And then what you want to know is what is to learn the force field that will allow you to go backward.
I see. Okay.
And the force field that allows you to go backward is the grad of the log of the PT of the Ornstein-Uhlenbeck process. You're right.
So then you know the force fields.
Right. You know the force. Okay, that's correct. So you know the force field in principle. So if you exactly use that force field, the bad thing is that you will always recover the data from which you started from.
Okay. So then do you change the diffusion coefficients or, I mean, what are the parameters you are fitting now?
So the idea, and here is where is the thing, is that you could say, okay, if the data is large enough, maybe you don't go back. And so what I told you is that whatever is the number of data, you can define a time at which the force field will bring you back to the data, which is normal, because if you use the perfect one.
Yes.
Now the thing is, the trick is that they don't learn the perfect one. What they do is that they learn an estimation of this. So doing something which is not the good thing, which is not the exact thing, they learn something that allows to generalize.
I see. Okay.
Okay? You see?
Yeah, maybe we can discuss.
Okay.
Yeah.
So this, I think, is one of the big questions really in the field is why actually diffusion models don't memorize in practice. Because what I told you is that if you do everything properly, so you optimize perfectly, and you learn perfectly the score, mathematically, you expect that you always get back the original data. But in practice, this is not what happens. And so there have been, let's say, several ideas out, but something that we understood, and again, it's the nice thing which is related to dynamics, low dynamics, is for in physical systems. So what we understood is that if you look at the loss function, when you try to learn this score, the loss function, it's a caricature, but it was come from the computation. The loss function is like this. So it goes down, and so when you do the gradient descent during the training, you first go to a point in which the system is not quite at the minimum, but it's let's say at a point in which the let's say the action has very, very slow direction, so the landscape has downward direction, but very, very flat. And you remain here for a very long time. Then if you push the training, at the end, you arrive to the solution which corresponds to memorization. But actually, for a very long time, you remain to the solution which corresponds to memorization. And this is what you see, well, this is an illustration, but we see it in numerics, is that if you look during the training, if you stop training at a certain time, then you have that, so this is the inverse quality, see this is the fraction of memorization, and what you get is that the system actually, well, first you have to train a little bit in order to get good images, but then you have to training really, really long time in order to see the memorization. And the time it takes actually to start to see memorization, scale with the size of the training set. Since you use big, huge training set, actually the system at the end will always memorize, but actually there is a very big window of time in which actually it doesn't, and because it stays in this almost flat region. So this is, well, just to tell you that studying the energy landscape or the training landscape, you can actually understand why the system that do not memorize. So what happens is that if you train really at the end, you will be here, but just stopping the training and using this neural network as a model for the score, you stay while you arrive very close to the generalization, so you get the generalization score. So, well, this is actually at least our interpretation. So I will conclude now. So I wanted to give you an idea of why there is a big connection between statistical physics and machine learning, why you can use methods which come from statistical physics to answer questions, central questions in machine learning. I would say that especially it's because there is a lot about dynamics, and dynamics is complex landscape. And then there are methods that have been developed in theory of disorder system, like replicas and DMFT, that have been very useful and are used right now to answer questions in machine learning. And so this is not just theory. I mean, you can also use obtain guidelines for practice from this work. And I think it's a very exciting research area, which is at the boundary between computer science, probability theory, and statistical physics.
Thanks, Giulio, for a fascinating talk. Questions?
So for finite data, is there true non-analyticity in this force function?
For finite data?
Because you are saying there is a phase transition, right?
No, you need, in order to have the phase transition, strictly speaking, you have to take, like in physics, the thermodynamic limit. If the number of data is finite, you have just a sharp crossover.
Luca?
Thanks a lot, a really super nice talk. So when we use ChatGPT, typically we refine our prompt, and we start from an initial version, and when we get something, say, okay, that image is nice, but could you blah, blah, blah. Can you tell us something about how this refining process is performed?
Yeah, so what you do is that it's a little bit, when I say that to give a certain kind of images, you have a kind of energy function that change. You have two wells. So when you give a prompt, you're just pushing up, for example, one well, and you are pushing down the other, so it goes more in one direction. So you're just changing the landscape, changing the, let's say, the relative weight of the different minima, which would correspond to the different solution that you can get.
But how that is done? Because it doesn't start from scratch. Again, you say, okay.
It's because when you give a prompt, so in already giving a prompt, between all the possible answers, so you should think that you have all the possible answers, all are equivalent minima. When you give a prompt, you're already pushing up many, which are all the answers that you don't get, you push down all the other ones. But among those, there are still many possibilities, so you put another prompt, and then you're changing it again.
Peter? 1 second, just that mic.
So you mentioned stochastic gradient descent, which is different from the thermal noise we're used to thinking about. How important is that? I mean, I think there are papers that have sort of discussed this, but what's the consensus? Does that make a big difference? Or?
Yes, so the answer is it's known to have a big difference. So if you train, if you try to minimize a loss function using Langevin or using stochastic gradient descent, mapping the same strength of the noise, actually Langevin is worst. And again, the idea is that stochastic gradient descent is, in a certain sense, is minimizing the test loss. That's the idea of many people. So since it's the test that you want to minimize, it's not the train. So this is why actually having this non-isotropic noise is good. So the Langevin has also noise, but this noise has nothing to do with the loss. So I mean, at least the intuition that I heard from many people is indeed. I mean, you could think in this way. Imagine that if you do a case which is called online learning, in which you never see the same sample. So in that case, if your batch is very large, you're really minimizing the test loss, really. So that's the idea.
So this transition to memorization, is that one step, or is there something more complicated?
One step, yeah. One step, you mean like one step per representation brick?
I wasn't going to commit myself, but
No,
but
it's really, so it's in a
but
sense,
it's somehow
really,
data dependent.
It's very similar in the sense that what you do is that when you to evaluate this force field, you could ask, okay, I take a typical sample in the force field, and I want to see whether this sample belongs to many. I mean, it can be associated to many other data, or just to one data. And so this transition from many, which is an exponential number, to just one is just really like the one-step transition. I mean, quantitatively. So this is how we did the computation.
Hi, Giulio. It's very likely that I didn't fully absorb, but is it the reason that it generalizes, is it also the reason that it hallucinates and sometimes creates outputs that are not?
I would say that, well, not so. When it hallucinates, is typically is because, I mean, here I say, okay, here is 0. Maybe if you are here, so it sometimes is going to hallucinate. So indeed, you didn't train it long enough in order to that it generate well. Or the other possibility is that if these two are close, but this generally is not the case, but if you didn't use enough data, then in order to don't memorize, you stop early, but then, I mean, it's not good, and so it can hallucinate.
Which one you want to ask the question? So, yeah, so this is a question related to the glassy landscape. I guess for glasses, going to the most stable glass is the challenge here. Are you saying that finding good enough solution, but not the best is good?
No, so the thing is, it's true that the analogy with glasses, it's not an analogy, it's really what happens, but it's a bit confusing. So the fact is that when you go back here, so the dynamics has force field that really brings you toward the minima. So it's really different from a glass in the sense that in the glass, you have a complex landscape, but then the force field that you use, I mean, it's what it is. I mean, it's just the grad of the energy, and this doesn't just send you on the minima. Here, the force field is sending you, well, in this case, if you are at low temperature like this, it's sending you toward the minima. So from this point of view, it's that you go very fast. So the only thing that you have to know is whether the probability distribution correspond to high temperature or to low temperature. But if it corresponds to low temperature, the dynamics, if you know the score function, it will bring you on very small time toward the minima.
Okay. Just to add a historical remark. Just to add to your historical background, I still remember the even earlier days than 2012, when the hope was that Spingler's model will be able to explain the brain, the human brain. And only Miguel Virasoro has remarked in those days that the only reason that they hoped that Spingler's model will explain the brain is because they failed to use their brain to explain Spingler's models.
No, I like it.
Yeah, so I'm trying to understand this particular picture.
Yeah.
At the end, when you randomize, there are two pictures here, two animals,
Yeah.
dog and a cat. And then when you randomize it, does the system know from which image it has, like, you know, you're giving probability distribution, and now you're training it with respect to two probability distributions, one of a dog, one of a cat, right?
Yeah.
And then eventually on the one on the left and one on the right, does it know from where, like, is it definite that it is going to go back to that particular image where it came from?
Okay, so if really you consider, so in the limit, so if we do it in the limit of very large dimension of the image, then yes, so it means that before this time, you cannot know, with probability 1/2, you go one way or the other. And after this time, with if, I mean, it's, let's say the fate of the trajectory is sealed. So it goes, so if you look at the, so let's say, I can tell you one experiment that we did. So what you can do is that you can actually clone the trajectory. Imagine that you arrive here, and then you use two different thermal noise from then on. So you will have two trajectory, and these two trajectory will end in the same class with probability 1. So it means really that you don't have a trajectory that, whoops, jumps on the other side after this time. So before this time, yes, you can have jumps, and here actually you cannot even say where you go. But after this time, you know, it's fixed.
It's directed to where it started
Exactly.
from.
Well, not where it's, yeah, where it's not really where it started, because it's a new trajectory.
Yeah,
But,
yeah. So, but it kind of
Yeah,
goes.
it's fixed.
Yeah,
Yeah.
okay, thanks.
We can take one more, one more question.
So in this case, we had one bear and a seaside picture as two training examples, right? So what if, say, we add one more, which is a picture in a bear in a seaside? Okay. So in that case, would the transition would be smooth instead of?
So if you have more, I mean, there are many things that can happen. So it could happen that, I don't know, if you could have a transition only on this lamp of trajectory, for example, or you can have, let's say, other transition on both lamps of trajectory. So you could really think like it was a tree, and the tree is constructing the property of the images. So that's how it works.
Any more questions?
It's bull.
So all of this is kind of determined by the force field, right?
By the force field, yeah.
So the force field determines where these transitions will happen, how many will happen at
Yes.
what time.
Yeah.
Okay, let's thank Giulio again for this presentation. So I understand there are two options now. Either we can sit and